Today we'll start with the last article of this chapter, which is Kirchhoff's laws. So let us see what are the Kirchhoff's laws and how we use them in questions. Basically, we have already been using Kirchhoff's laws in questions, but we had not specified them. Now we're going to specify Kirchhoff's laws, their statement, and then use them in questions as well. So, what is Kirchhoff's first law? It says that, for example, we have 11 ampere of current entering a point A. From point A, the current is divided in two parts, I2 and I3, 7 amperes and 4 amperes. In simple calculation, we can say that the current which is entering the junction must be equal to the current that is leaving the junction. This is Kirchhoff's first law. It is called, in a specific wording is that it is the algebraic sum of current entering a point in a circuit is equal to zero, but we can use the simple statement as well that the sum of current entering a point in a circuit is equal to sum of currents leaving the point. That is, I1 should be equal to I2 plus I3. And if I take I2 and I3 to the left hand side, it becomes the algebraic sum of the current. Algebraic sum means that the current which is entering it is taken as positive and the current that is leaving is taken as negative. If you add them up, you will get the answer equal to zero. So first statement can be used or second statement can be used. Both are for Kirchhoff's first law, and it is also called law of conservation of charge. If they say which law states law of conservation of charge, it is Kirchhoff's first law. So you should know the application, you should know a statement, and you should know that it is law of conservation of charge. So this is Kirchhoff's first law, that whatever is the current entering a point, it should be equal to the current leaving the point at that junction. Kirchhoff's second law. Again, we have been using it. We have two resistors in the circuit. We have ammeter, we have voltmeter, and we have EMF of the cell. In this circuit or loop, the sum of EMFs must be equal to the sum of the products of the current and resistor, or sum of the potential differences across all the resistors. That means V1 plus V2 should be equal to the EMF of the cell in a loop, in a closed circuit. This is called Kirchhoff's second law, and it is also called law of conservation of energy. This is your Kirchhoff's second law, but we have been using it in in the simple questions as well, in which we used to say that EMF is equal to sum of potential differences. You can use the same statement. It is also called law of conservation of energy. So let us see some of the questions in which we'll be directly using Kirchhoff's laws. EMF definition: energy converted from non-electrical to electrical form to drive a unit charge around a complete circuit. Internal resistance: it is the resistance inside the cell which causes loss of voltage or loss of energy inside the cell. Now we have a closed loop. In this case, there are two batteries or two cells connected and they are in series. And there are three resistors, 0.1, 0.2, and R is 3.3. So this is a single loop. There will be a single current in the circuit. And according to Kirchhoff's second law, sum of EMFs must be equal to sum of the sum of the potential differences across each resistor. We'll just add the EMF, but in this case, observe this is 12 volt, this is 3 volt. Positive is connected to positive. Now, in this case, they will be opposing each other. Wherever positive is connected to positive or positive is connected to negative, in case positive to negative, they add up. In case of positive to positive, they oppose each other. So we have an EMF equal to 12 minus 3, EB minus EA. Current will be same, multiply by total resistance of the circuit. Put the values 3.3 plus zero point 0.1 plus zero point 0.9 plus zero point 0.2. So 9 divided by 3.6, you get the answer as 2.5. So the current in the circuit is 2.5. Power transformed by the battery B. Whenever we say battery, we use the formula VI because that we know the voltage of the battery and we know the current in the circuit. So straight away use VI. So this much power is given by the battery B. In the next part, they ask us the power loss in the resistors. Energy loss per second is power in resistors R and internal resistance I square R. In this case, R will be taken as sum because each resistor will have the same current. We know the current, we know the total resistance, I square R, simplify and you get the power. Observe, power supplied by the battery was 30 watt, but power loss in resistors is only 22.5 volt, joules per second. Where has the remaining power gone? Can this circuit be used to store battery? Yes, of course, because the power supplied by cell B is greater than the power loss in the circuit in resistors, so the remaining power will be stored in the cell A. Again, they have asked us the definitions of EMF and potential differences. Whenever they ask you to compare them, always write down the proper definitions of both the quantities. EMF and potential difference. Now they have given a circuit in which there are different branches. There are two EMFs attached. In one of the branch is E1, the other one has E2, and there's a third branch in which we have resistor R3. We have to find the relationship between I1, I2, and I3. So we have to choose a junction where all the three currents are entering or leaving. I choose X. Observe I1 is entering by its arrow. I2 will also be entering from the fact that it is positive E2 connected to X. So I2 will also be entering and I3 will be leaving. So my relationship is I1 plus I2 is equal to I3. Now we have a loop X, B, C, Y, X. We only be considering this loop. And we will only be seeing in this loop what is the value of EMF and how many voltages are being dropped. So in this loop, there is only one EMF E2. Some of the voltage will be dropped against R2, which is I2R2 and I3R3. So to add them up, sum of potential differences will be equal to sum of EMFs. Only one EMF, so E2 is there. In the second part, the loop is AXYDA, the above loop. In this case, we have two EMFs. One of them is bigger, just like the question we had did in the previous case. 12 minus 3 किया था हमने. इसी तरह इनमें से हम एक को बड़ा EMF कहेंगे, दूसरे को छोटा कहेंगे. So we can say E1 minus E2. Then the current will be driven by E1. What does that mean? It means that the current of E1 will be taken as positive, whereas the current of E2 will be taken as negative because now the current will be driven by the larger battery. So in this case, it will be E1 minus E2. We'll take the current of E1 as positive because it is the larger battery, and the current of E2 is negative because the main current is driven by the larger battery. So the current of the smaller battery will be taken as negative. Therefore, my answer will be minus I2R2. So you will only consider the loop that is being mentioned and then use that loop and apply Kirchhoff's law that sum of EMFs is equal to sum of the potential difference in those resistors. Okay, let's take another question. We have two branches. On one branch, we have a switch S1. On the other branch, we have a switch S2. If S1 and S2 both are closed, these two resistor branches will be parallel to each other. But R and R on one branch will be in series. But before that, if both the switches are open, what is the combined resistance? If S1 is open, no current can flow from this side. If S2 is open, no current can flow from this side. If no current can flow, then the resistance is infinite. So if both switches are open, there will be an infinite current, infinite resistance. If S1 is open and S2 is closed, it means no current will flow from this side, but it will flow from the other branch. And in this case, both the resistors will be in series. So your total resistance will be 2R. If both switches are open, if both switches are closed, this is 2R, this is 2R, and both of them are parallel to each other. And if they are parallel to each other, then their total resistance will be 1 over 2R plus 1 over 2R. Simplify that by taking reciprocals, and your combined resistance comes out to be R in this case. Okay, now we have a circuit here. Two batteries are being attached. We have two branches, NPK and NQK, and there's a third branch, NK. We have different currents in different branches. Identify junction, like I choose junction N. I1 is entering. I3 will be entering. I2 and I4 will be leaving. In this case, it will be I1 plus I3 equal to I2 plus I4. Okay. So I have I1 plus I3 is equal to I2 plus I4. Now we have a loop. NKLMN. N K L M N. We have two batteries E1 and E2. We have only one resistor. And there is no resistance in this path, that is KLMN. So if we take E1 as larger battery and E2 is smaller battery, then the current of E2 will be considered as negative. So we have E1 minus E2 is equal to minus I3R. Remember, जो छोटी बैटरी होती है उसका करंट हम नेगेटिव देते हैं, तो यहाँ पे स्मॉलर बैटरी वी आर कंसिडरिंग एज E2 because E1 minus E2 means E1 is the larger battery. Okay, second loop, NKQN. Only one cell, E2, I3 into R, and we have two R's. Both of them have same current, I4. So I4R plus I4R. That is 2 times I4R. On the other hand, if we had taken E2 minus E1, then I3R will be taken as positive. So that depends which battery we are considering to be larger. It is our choice. अगर हम E1 minus E2 करेंगे तो minus I3R होगा, और अगर हम E2 minus E1 करेंगे तो I3R होगा. Both answers will be considered to be correct. Okay, let's take another question. Similar one. Choose a junction. For example, Y. I3 is entering, I2 is leaving, and similarly, I1 is also leaving. I3 is equal to I1 plus I2. Now we have loop W X Y Z W. W X Y Z W. Now this is the outer loop. We just neglect the inner one. E3 and E1 are connected positive to negative, so they will simply add up. E3 plus E1. I3 R3, I3 R4. And in case of R1, we have only I1 current, so we have I1 R1. Okay, second case, YZWZ, YZWY, YZWY. If you observe, E2 and E1 are connected positive to positive or negative to negative. So one of them will be considered as smaller battery. For example, if I say E2 minus E1, I2 R2 will be positive, but I1 R1 will be considered as negative because E1 is to be considered as smaller battery in this case. So you just have to write the equation properly. Generally, Kirchhoff's law requires that. Okay, another question. We have arrangement of resistors, two parallel, and R are in series with these two parallel. A and C. A and C has a straight way only one resistance, which is R. B and X. B and X, we have two resistors in parallel. So 1 over R plus 1 over R. Simplify that, becomes 2 over R. So your combined resistance is R by 2. A and Z. This is R. This is R by 2. This is R. So it is R plus R by 2 plus R. So your total resistance comes out to be 2.5 R. Again, we have a bit circuit which we have three branches. First of all, I1, I3, and I2 are the currents which are entering or leaving a point B. I1 is entering, I2 is entering, and I3 is leaving. So it will be I1 plus I2 is equal to I3. B, C, X, Y, B. In this branch, we have only one cell, E2, and we have two resistors, R and R. This has I3 current, this has I2 current. It will be E2 is equal to I2R and I3R. Then we have A, B, C, X, Y, Z. It means the outer loop. We have two EMFs, E1 and E2. Again, it's your choice. You can take E1 minus E2 or E2 minus E1. If I take E1 minus E2, then I1 will be positive and I2 will be negative. So considering this, we can find the equation. Considering E1 is the largest cell, its current will be positive. E2 is a smaller cell, its current will be taken negative. Okay, now we again have it is slightly complicated, but just keep in mind clearly that what is Kirchhoff's laws. So I1 is entering point B, I2 is leaving point B, and I3 is also entering point B. It will be I1 plus I3 is equal to I2. Now look at the branch they are saying. H, B, J, F, G, that is the upper branch. And in this case, BJ, rather B to F, total resistance is R2. And it is the midpoint. So BJ will be R by 2 and JF will also be R by 2. Only BJ has the current I2. remaining circuit, whether on the left hand side or right hand side, it will have the current I1. So we have EMF E1. I1 will be creating potential difference across small r1, capital R1, and R2 by 2. Only the voltage that is dropped across R2 by 2 BJ is I2. So I1 will be multiplied by all the resistors plus I2 R2 by 2. So we just use a path, and in that path, the current will only flow in that path. It will not be uh, leaving that path as it is. Okay, next loop is H, B, C, D, J, F, G, and that means that it's the outer loop. We'll be neglecting BJ. E1 minus E2 or E2 minus E1. Generally, E1 is larger one. If I write out E1 minus E2, I1 will be taken as positive and I2, I3 will be taken as negative because E2 is smaller cell. So I1 will have the same R1, R1 and R2 by 2, but for small I2, I3, R2, it will be taken as negative. Clear? Okay. Next is it is a midpoint. Whatever is the voltage across BJ, if it is equal to E2, the current will be zero. This is potential divider circuit, and we are using it as a potentiometer. The voltage BJ, suppose it is 2 volts and E2 is also 2 volts. Then this is positive, this is positive. So net EMF will be zero and there will be no current. So if BJ voltage is equal to E2, the current will be zero. But if we change the value of J, the potential difference BJ will change, and the potential difference between the 2 points will also change. Therefore, the current will also change, and ammeter reading will also change. So logic is that BJ is the voltage that is being part of the total EMF. If that voltage is equal to E2 and it is opposite because positive is connected to positive, then there will be no current. But if either of the EMFs are greater, then there will be a current. That's the logic here. As the length of resistance changes, so difference between the potential across the wires and E2 changes, so the current will also change. We have E1, we have E2, and we want to find out the EMF of this E2. This is called a null method. Basically, what happens is that if AJ has the same voltage as E2, galvanometer will show no current. The logic is same that if the potential difference is zero, the current is also zero. Now, for this, we have to find the length AJ and find the value of EMF. If we have 2 volts and it is, we have to find the voltage across AB. We can find it by using the simple formula V is equal to IR, and using that, if the galvanometer shows zero resistance, zero current, it means that the voltage which is developed across AJ will have the same value as E2. And if it has the same value, then the galvanometer will show zero current. For example, we have uh, 100 centimeters in length and it represents 2 volts. If 40 centimeter means we have 40 centimeters, 1 centimeter will be 2 volt divided by 100. In other words, 40 centimeter means that it will have a voltage 0.8 volts. And if the current is equal to zero, if the current is equal to zero, then the EMF of E2 will be also equal to 0.8. I'll just add that. So this is the logic. If we have a zero null method says so that if we have 2 cells and we make a potentiometer out of it and we attach the second cell in such a way that we can have a variable contacts. So we just move this contact and wait until we get zero current. And when the current is zero, in that case, it shows that the potential difference AJ is equal to the EMF E2, and now in this case, the current will become zero. So this is called null method to find the EMF of the set. This was what I was referring to in the last question as well. Okay. So this completes our topic, and tomorrow, inshallah, we'll be starting waves.